This is actually a slideless presentation. I will basically be doing everything, actually showing the real GitHub issues and source code. So my presentation is all about a real thing my team and I had to do in our roles as open source software maintainers on the Akka.net project. This is all about how we inadvertently introduced a memory leak. A user who also is using dotMemory was able to diagnose it, and how we were able to reproduce it, fix it, and then use dotMemory to verify that we had indeed solved the leak. So just to give you a little bit of context on where this came from and a little bit of sort of background of the Akka.net project. Akka.net is an implementation of the actor model in .NET. It's a port of a Scala project by the same name, Akka originally. And we handle all sorts of different workloads. Akka.net can scale down to running on a mobile app or running in an embedded device. It can scale up to running, giant clusters that have thousands of nodes in them on a cloud system like, Azure or AWS. This specific memory leak came from our persistence system. And this is a blog post that we wrote about a scaling technique that we've used to allow Akka persistence query, which is basically what you would use to take data that is stored using Akka actors. It's all event sourced to an append only log that is scoped to each specific actor that basically owns an entity inside a system. You can use Akka persistence query to project all those events into new forms. So, for instance, you can use it to create materialized views or projections or indices, that sort of thing. And we introduced a technique into our sort of, it's now legacy, Akka persistence implementation for SQL Server. We introduced a scaling technique that basically allows us to run hundreds of thousands of concurrent queries that all work by polling the underlying event logs. Well, in order to make sure we don't saturate connection pools and end up swamping the database server with lots of concurrent queries, we introduced a token bucket throttling system, which really isn't the thing we're going to talk about today. But this is where the leak came from, was introducing this token bucket throttling system. Um, Long story short, we had an old Akka persistence SQL implementation dating back to probably 2015. We replaced it with sort of a unified solution that uses link to DB to go ahead and do high performance queries. This was actually developed originally by like a power user for Akka.net. And we eventually incorporated it and made it the first party sort of replacement for all of our SQL based persistence. We wanted to basically port the original scheme that we had implemented back in 2022, 2023. Back late last year, we wanted to bring that same throttling implementation into the new persistence SQL plugin. And this plugin has thousands of users that are running. In some cases, they might have event stores that have billions of events stored in them. So, fairly significant size around this plugin. So we ported all of this code over and we packaged it up into a release. I think this went into, I'll get into the code in a little bit. Well, actually, I guess I'll go ahead and show the relevant code now. The relevant code here, if I pull up Writer, this is from the same repository we were just looking at. This is all the different messages that play into our token bucket throttling system, which basically means you request a token to be able to execute your query. There's a single actor that runs in a process that keeps track of all the tokens that have been issued, and it will only basically allow n number of tokens to be in use at any given time. A token will be returned when a query completes, and that completion could be failed or it can be successful. We don't really care as far as the throttler goes. We just need to make sure there's not more than n number of concurrent requests. That's the basic gist of all this. Well, this is the query throttling actor, and this actor keeps a linked list of all the pending requests. And down here, it uses a little bit of code to keep track of where the actual requests are coming in from. And so if we get a request from an actor to execute a query, we're going to use a built-in, this is an important detail because it's going to come back to bite us later. We use a built-in Akka.net feature called Death Watch. This allows actor A to subscribe to actor B's life cycle and get a notification back if actor B is dead. If actor B dies before it had a chance to return its token to us, we need to go ahead and add that token back into the token pool. Otherwise, what you might have happen over a very long period of time is you might have some tokens that never get returned, and eventually the querying system will just stop working if that happens. So, this is a resiliency mechanism designed to prevent that type of exhaustion case from happening. We had thought all this through before we implemented it. So that's sort of the background here. So we introduce all of this. Lo and behold, we ship this in a new version of Akadot Persistent SQL. And maybe 2 or 3 weeks after we ship it, we see this GitHub issue appear inside the repository. And this user, production user using Akka.net, and he noticed on the staging environment, this is a graph of the available memory inside the system. And you see that the available memory is gradually ticking down over what appears to be looks like, about a week or so worth of usage here. So it's gradually starting to tick down. This is in their staging environment. So this is presumably not even doing any live work. And you're still seeing the memory usage tick down. Sometimes in a non-live environment, it's actually easier to notice these types of slow moving memory leaks. But for that reason, you don't have the variability that you get with a production environment where the load can shift and change quite a bit. In a QA environment, you're more or less running the same configuration and same orientation that you might use in production, but without a lot of the live traffic. So they were able to notice their in memory, their available memory gradually creep down. And after inspecting, basically the virtual machines, this is all application insights data up here. The customer was able to detect that there was a whole bunch of data accumulating from the Akadot Persistence journal that uses this code. And he produced these graphs from dotMemory here. Okay, the first thing you should notice if you are trying to inspect a memory leak is having some awareness over which objects have a long lifespan, which objects have a short lifespan. Anyone who's done .NET for a significant amount of time should see that if you have a bunch of task objects being rooted inside your application, rooted means they're being retained by something, you have a black and white, absolute, no ambiguity memory leak going on. These are supposed to be very short-lived objects. Tasks, by their definition, are meant to be temporary. Other objects that might share the same sort of like short life cycle might be something like a cancellation token or something else. These are objects that are not supposed to be growing in memory usage over a long period of time. You're basically supposed to have them and then get rid of them once you're done using them. Well, there was a second object in here that this isn't the user's fault. This is sort of more Akadot internals. This future actor ref down here. This is a specific type of one-time use actor that exposes a task of this type here. It's meant to basically allow us to implement request response inside Akka.net. These actors are supposed to live for exactly one request. They're extremely lightweight. Well, the fact that he's got 250 megs of them sitting around and he's got nearly, twice that amount of tasks tells us that we definitely have a memory leak, and it's probably stemming from this future actor ref right here. That's all without us even firing up dotMemory ourselves, just from the end user profiling one of their own virtual machines using dotMemory to produce this graph. So he's already put together a pretty compelling story that gives us a high degree of confidence that there's a memory leak. He also very helpfully, by the way, if any of you want to report a bug in an open source library, reporting this type of information, I was on this version, then I moved to this version, narrows down the search radius on what we need to do to investigate a bug by a lot. Makes it very easy to jump right in and figure that out. So the long and the short of it, he did some research on here. Myself and Arcatufus, whose real name is Gregorius, we are both full-time employees who work on the Akadot project. We were able to look at it. He even submitted a bug reproduction, and I submitted one as well, which I'll go ahead and fire up right here. Let's see. This reproduction is really, really simple. And this is the first thing you have to do to try to grab a memory leak. You've got to have some way of observing it somehow. Those charts and graphs the user submitted are helpful, but you really need to be able to reproduce it and observe it yourself. not necessarily because you don't believe the user that there wasn't a memory leak, but because how are you going to know if you fixed it otherwise, right? So you need to be able to have some way of determining whether or not after you introduced your fix, did it actually solve the problem. So that's the real importance of having a reproduction is being able to verify the fix. That's just as important, if not more important, than being able to verify the existence of the bug in the first place. You kind of need it for both parts. So this is a really basic Akka.NET application. We just fire up a headless service here. We're going to fire up Akka.persistence, and then we're going to create a really basic Akka.persistence query where we're just going to go ahead and iterate on the event journal. Now, what's really interesting about this reproduction is this query will never return anything because we're actually not writing any data at all to the journal whatsoever. We're simply trying to read from it. And this all events query will essentially try to pull the database every, I think by default, maybe it's every few seconds. It'll go ahead and try to pull the database for new records and return a result. So if you can see memory growth from this sample where there's not even any real results being returned, that's going to give you a really clean data signal that will help you both verify the existence of the bug and verify that the fix worked. So this is the part where I'm going to bring out dotMemory. Now, this is an old snapshot here that I took from this code sample, but I'm going to go ahead and create a brand new one real quick just to show you how to do that. So, and then let me just zoom in since dotMemory doesn't support a native zoom here. Let me do this real fast. All right, here we go. So this is dotMemory. I use this tool anytime we have to do a memory leak. The built-in profiler in Writer also can give you a lot of this information, but dotMemory makes it a lot easier to kind of flip between doing comparisons from one version of the application to another. And so this is kind of my daily driver if I need to investigate a memory leak. So what I've done here is I've added a configuration to simply run the debug build of my executable on .NET 9.
Aaron, sorry to interrupt there. The Zoom hasn't worked on the stream, unfortunately.
Oh,
Um, I think it'll be okay if you could just describe a little bit better when there's something which is going to be a bit smaller. I think we'll all be able to manage without being able to read every detail there. But just to let you know, I'm afraid it didn't work.
well, gosh darn. All right.
Exactly.
But the basic gist of this is that I basically just configured this to point directly at the build output. I think you can also actually add as a process down here. I think you can actually add the let me see if you can do this still. Any external .NET process, self-contained application. I thought there was an option for being able to add a .NET, like a .NET run using an actual build project. Looks like maybe there isn't one anymore. But either way, this is sort of what I configured to set this up. And then we're going to run the profiler here. And I'm going to run this with full profiling because this is just a silly little reproduction application. I don't have any real application performance to interfere with. If you were profiling against like a running instance of your application on a VM somewhere, you might want to use sampling instead so the profiler doesn't tax your application as much. All right. So let me go ahead and start this. So I got the application up and running here. All right, there we go. And you're going to go ahead and see the memory usage just start to tick up just a little bit, and it'll come back down with GC usage. And if I go ahead and I get a snapshot here, and I'll grab another snapshot here, these numbers are going to kind of stay relatively stable. Now, one of the things that's a little tricky with this bug is that this is actually a very slow moving memory leak. It's only going to allocate one new object every 3 to 5 seconds or so. So you might have to have the application under observation for a fairly long period of time in order to be able to get all of the relevant data that you need here. Now, since we're doing a live presentation and it would be pretty boring to sit here and watch this application run for 30 minutes to get the data we need, I'm going to go ahead and turn dotMemory off, and we're going to look at some older workspaces where I let the thing run for hours. Like I got up on my, I basically had this thing running on my computer after I went home for the day, and I came back and observed it the following morning. You can configure in dotMemory the ability to automatically take snapshots after certain thresholds have been breached, and so the application I think ended up not the application dotMemory ended up grabbing like 3 or 4 snapshots for me. So this was I believe one of the ones we were just looking at. All right, so here we go. So this is where the problem is stemming from right here. So I can see that we allocated, in terms of the total number of objects, let's see. We basically are gradually accumulating these future actorefs, query grant started, and task completion source query grant started, all right here, all three of these. Whoops. And so this is basically the total number of new objects we had. This is the delta between them. And this is where the memory leak is ultimately coming from, is these three items. Now, these three items are all actually related to each other. The task and the task completion source are both created by the future actor ref. That's a internal implementation detail. But you can really clearly see the memory growth beginning to happen here in this analysis. And if I go and I take a look back at the basically like the similar retention down here, I can see that basically what's happening is the SQL read journal is going to start this async operation down here, and part of that is going to end up being building this dictionary of actor references. Huh. Now, this dictionary right here has a name on it, watching. We took a look at some code a little bit earlier. We looked at our query implementation. If I go and pull up writer again, let me go this. We saw this basically method get invoked a little bit earlier on an actor reference. Huh, watch. Does this have anything to do with this watching dictionary that is rooting all these future actor refs? Well, if we assume that the developers named these things competently, it would be good to assume that, yes, there probably is a relationship between these two. So let's take a look at the underlying source code in Akka.NET here. Well, in fact, you know what? I'll go ahead and just pull up another writer instance here. And we will go to, I actually know from memory where this code is because I've had to work with it for about 12 years now. Akka, actor cell death watch. And let's look for watching. In fact, I'm actually pretty sure it is in this data structure right here. Watching, and it is somewhere around here, the watching stuff. What is ultimately happening here is that we are watching these actors that are being sent in to the throttler requesting permission to run a query. This request query start, I scroll down here. This request query start is being sent. In fact, let me break this out into multiple lines here just so it's a little easier to read with the zoom. What's happening here is that this query permitter, this is our throttling actor designed to help prevent the database from getting flooded with connections. We're using in Akka.NET what's called an ask operation. This ask operation creates a temporary one-time use actor. We send this message to this actor, and we expect this reply back within this stretch of time. If we get a different message back or we don't get anything back, we will go ahead and throw a operation timed out exception, and that will cause this operation to fail, etc. This is just basic sort of request response on top of actors. That's all that this is here. So this creates a temporary one-time use actor. That actor is being, if I scroll down here, death watched by the query throttler. And as we can see here in the actual data that we've gathered from dotMemory, we can see that there's a dictionary of watched entries that is getting bigger and bigger and bigger, retaining these future actor references. And so what is really happening here is that this wasn't a bug at all with Akka Persistence SQL or our query throttling implementation. As we discovered in our investigation, as a result of the data we got from dotMemory, this was actually an ancient bug, and by ancient, I mean over a decade old, inside Akka.NET's handling of Deathwatch for this specific actor type, the future actor F, the temporary one-time use actor. This is like a special case actor that we only use for doing request response. And it gets killed immediately after it's done being used to fulfill that task. So that actor and all of its internal dependencies, namely the task completion source, were being retained indefinitely by this death watch function. That's why the memory was gradually building up. And that's why dotMemory was able to detect it occurring inside that dictionary here. So if I go back to our investigation here, you can see basically where we are discovering all of this in real time. And as I scroll down to our main Akka.NET repo, let's see if I can find the actual pull requests that close this. Yeah, here it is. All right, here we go. We found the real bug and the real fix here. Junior says he's lost. Okay. Long story short, from a componentry perspective, when you do an ask operation inside Akka.NET, in fact, maybe it'd be easier if I showed that code. If I take a look at, I guess it would be futures ask. Let's go down here. This is where the memory leak's coming from. And this is less about dotMemory. This is more about being able to track down a very old and very cantankerous bug in Akka.NET. When you do an ask operation, you just see a task. That's all you see is the end user. Let me get it back. Akka.NET has to do some internal machinations to make sure that that easy, simple looking task actually gets performed correctly under the covers. And what we do here to do that is we create what's called a future actor ref. Down here, go ahead and pull that up. This future actor ref is a single use actor. This actor gets completed. If I go back to Akka.NET Persistent SQL, this actor gets completed down here when we basically grant, if I go down to this, when we tell that actor this message, that causes the task to complete. And that allows the actual actors that want to run their SQL queries to continue. And that kills that future actor ref. When someone wants to watch an actor ref to get notified if that actor is dead or alive, which is what we were doing earlier, that actor is supposed to send a completion signal. I have terminated once they're done. And that causes the entry in that dictionary to get released. Well, the basic problem here, if we scroll down, this is where the bug was inside our system here, which is that when someone wants to death watch an actor, it's basically setting up a little subscription. That subscription begins with a watch message, and that subscription gets resolved with a terminated message where basically says, okay, you wanted to know if I've stopped. I'm going to send you that stop message here. The problem that we were having that we fixed in that pull request is that if I scroll down here, this is the actual PR where we fixed the issue. That's a unit test. Let me go down to just actorref.cs. We were never sending a death watch notification back to anyone who tried to death watch a temporary actor, this future actor ref here. As a result of that, I go back to our actor cell. As a result of that, the actor state keeps track of who are all the actors I'm waiting on death watch notifications from. That dictionary was growing indefinitely large over the span of like weeks in this case, which added up to gigabytes worth of memory. And that's what you can see inside here. You can see the actor cell maintains a reference to the actor state. The actor state contains a dictionary of all the different actors that are being monitored for death watch. And that dictionary had a growing set of future actor references that should be popped out of the dictionary and deleted when the tasks complete, but weren't. So in other words, dotMemory helped us find a bug that was like 10 years old and probably affected a ton of other end user applications that entire time. But we didn't have a really good signal on it until a user observed it in their environment, used dotMemory to produce a chart for us, and then we were able to go and reproduce it ourselves. And if I go and grab, let's say, like our most recent profiling on here, or if I went ahead and I ran profiling on the latest right now, you would see that dictionary essentially never grows in size anymore. It's more or less a dictionary that has fewer than 30 entries at any given time, but depending on the number of in-flight tasks that are actually being monitored. So dotMemory made it really trivially simple for us to actually find a bug that has been in Akka.NET for a really long period of time. Question from Guys: was that an oversight, or did you figure nobody would ever want to death watch a small one-time actor? I think it's a combination of both. It's an oversight in that all actors implement this iActorref interface, and the death watch contract is supposed to be able to work on all of them, right? So that's something that we should be able to fulfill and support inside the system. So that's where it was an oversight. Where it was kind of a where, and also the other area where it was an oversight was we never tested that scenario with future actor Fs specifically before. And we also kind of figured in terms of our prioritization, that was a pretty small potatoes thing for us to look at. It wasn't until we built our own internal component that depended on that functionality working reliably where it became a really critical issue that merited the attention that we ultimately gave it. So yeah, bit of an oversight, and bit of also and not important enough for us to really dig deeper, because it turns out we did have some handling around Death Watch for future actor references. The problem was it wasn't implemented correctly. So the oversight probably came really from a lack of testing more so than a lack of foresight, if that makes sense. Let's see. We were able to go ahead just to kind of wrap up our story here. If I go back to the original memory leak, which I guess would have been, let me go pull up the actual issue again here. Oh yeah, here we go. We were able to go ahead and patch the memory leak in the next version of Aqueduct Persistent SQL, so 1.3.8. And Luca, I think, chimed in our Discord and let us know that the issue was completely resolved after that. So using dotMemory, we were able to, but us and the customer using dotMemory, we were able to discover the issue. We were able to figure out precisely where it was happening and fix it in a relatively short amount of time overall. So the overall amount of legwork we had to do to investigate a problem like this was fairly small. And dotMemory really is kind of the workhorse that makes it easy for us to do that. We have had other memory leaks. That's kind of the nature of our technology. We're doing distributed asynchronous systems that also involve things like databases or working with Kafka or whatever. So it's a fairly complex open source library in terms of like all the hardware and all the infrastructure that's kind of running underneath it. So we've had other memory leaks before, and we've used a very similar process with dotMemory. This was just a very clear cut example that made it easy to kind of tell a complete story. So thank you all for your attention and your time. If you have any questions about any of this, you can hit us up on the Akadana Discord, or you can find me on X under Aaron on the web. Otherwise, I'll be happy to take some more questions.
Yeah, hi Aaron. That's a fantastic story. I do like a good war story when you hear the things that we encounter every day, but we don't often do a presentation about them. So it's nice to hear it how it actually happens.
Yeah, same. I have a very soft spot for performance and memory profiling, so I had to jump on and ask you some probing questions. I really appreciate your tip on the largest size for what was it? Uh, task and cancellation token,
Yes.
right?
Yeah.
That is such a good, simple takeaway. It's going to stay with me, I think. But my question is, does that rule of thumb apply to every kind of .NET app, or
You
is
know,
that maybe
it's
specific?
so
No,
most
please go
memory
ahead.
leaks are a lot more subtle than this one. Seeing a task get rooted is just like it's like a screaming red klaxon that like something stupid is happening inside the code
Right.
somewhere. You're usually not going to get that lucky. um, More often than not, it's going to be something like a string or whatever that's building up where you basically like I think about this a lot in the context of actors because, like, one question that someone might have is like, well, how did that dictionary get so big over the span of like months, right? And the answer is that
Mhm.
actors live forever by default. They are long-lasting and stateful objects typically. You can have very short-lived actors like the one that caused this leak, but typically they tend to be big objects for the most part. Not big, but like long-lasting objects. So I think about the sort of life cycle of state quite a bit as part of my day-to-day job. If you're building an ASP.NET Core application where you're used to everything being highly transient, where you've got, a request, it gets processed, you send a response, and you're done, might be a little bit, it might be kind of a new growth area for you to kind of start leaning in and thinking about, okay, what parts of my application actually have life cycles and lifespans where objects might persist across, several different calls, and how do I know if they're leaking or not? It becomes a little bit more of a question you're going to have to set up an experiment for, like we did, with where you need some way of observing it happening in the wild. And one thing I was kind of lamenting actually in our Discord chat the other day with some users, which is we have a user who's trying to track down a really high like burst CPU usage issue right now. That's more of a .NET Trace thing rather than .memory. Trying to track that down right now. And I mentioned to our users, I was like, it's so regrettable that we've kind of moved so much of our application workloads onto like platform as a service platforms like App Insights and container apps. Is actually being able to profile a live running application is really useful. Those managed platforms make it extremely onerous to do that. Whereas being able to just RDP into a VM and set up, dotMemory to go and monitor one of your QA nodes, which is what this user did, is relatively easy by comparison, but you need to be running on more like infrastructure as a service to do that. So it's kind of one of those underappreciated trade-offs, I think.
Since you mentioned profiling in a production environment, I'm just curious, what would be your advice to folks who are maybe new to profiling? How would you advise to go about, should they, when profiling in such an environment, should they start broad or like go straight for the main suspect, so to say?
That's a good question. I think what this user did, which is profiling on a staging environment where you have all the same bits that are running, but not nearly the same level of traffic, that would be the ideal, because you're free to go full bore and turn on all the profiling options, be as aggressive as you want without impacting live customers. But the problem is that in some environments, the issue might only occur in production because of that
Mm,
variability in that live traffic. In which case, what you should
yeah.
do is attach the profiler to your running executable and use sampling. Use some of the gentler profiling methods that aren't as likely to steal CPU, memory, and other resources that way. The other thing I would caution is you need to try to make sure you have enough headroom on those services where the profiler is not going to cause a side effect that renders the service unavailable. So if you're running at 100% memory utilization, probably not a great environment to try to profile. You probably need to scale vertically or horizontally or something first before you attempt to do it. So that's just sort of those are pretty broad strokes, things to kind of bear in mind about trying to balance observability with, but this is like a type of observability with your actual application's needs for being able to serve customers.
I think it's
Thank you.
yeah, I think it's a very under real. I liked your point there about it being the oh god, I can't speak. All of a sudden, it's falling apart. The, the idea of having overhead, enough space, enough headroom to do the actual sort of tracing is really important as well. We kind of sometimes don't remember that we're on these managed platforms which have been given a limit
Mhm.
of the memory, and you live within that budget that you've got, and it's very easy to forget that. So that's a great tip as well.
Yeah, absolutely. And I think, other things that kind of make profiling somewhat difficult and awkward, honestly, Docker is a big one because now you have this whole like the whole isolation and reproducibility of Docker is great. It's what makes deploying with it so easy. But being able to actually profile an application running inside a container requires a whole bunch of extra steps you wouldn't need if you're just running on a virtual machine with a Windows service somewhere, right?
Mhm.
So
Mhm.
these are some trade-offs you don't think about until you have a problem, right?
Yeah,
Um,
exactly. It's sometimes hard to plan for these kinds of events there. Actually, I mean, that comes back to the point I wanted to pick on up on what you were saying about actors live forever by default. With the sort of seeing this, have you kind of considered that maybe you should change that idea? That perhaps is it worth introducing a policy where actors actually get terminated by default, and you kind of have to do the opposite?
So, like Microsoft Orleans, for instance, has this virtual actor approach where actor identities live forever, but the actual actor instance itself, the thing that uses memory, can kind of pop in and out of existence depending on when you need it. We have an implementation of that same idea in Akka cluster sharding, which is where if you're building a distributed system where you need to manage like thousands or tens of thousands, or even in some cases, millions of entities, cluster sharding will do that. And by default, it'll go ahead and kill any entity that hasn't been sent a message in 60 seconds, I think is the default. And that's configurable. So that's sort of for managing, let's say, a large amount of state over multiple processes. We do have a solution for being able to make sure you're not persistently building up memory over time. Otherwise, we have some mechanisms that users can use. We kind of are not very Akadon, not very opinionated by default. That's one of a big design differentiator for something like Orleans, for instance, where actors by default live forever, but we have a tool called an idle, like a receive timeout, which is basically like an idle timeout where you can send yourself a message if no one's tried to contact you within X amount of time. And typically actors will shut themselves down when that happens. But we kind of leave that up to the discretion of the user rather than trying to guess what they want, if that makes
Mhm.
sense.
Yeah, yeah, absolutely. Um, uh, and I think a bit of a follow up on that one as well, and is sort of how often do you use tools like dotMemory and looking for traces? Do you have any processes in place to actively look for issues?
Yes, we do. So we don't have anything like an automated CI/CD pipeline for looking at memory per se. But what we do have, we have a pretty big suite of benchmarks built directly
Mhm.
into the core Akka.NET project. We have two different types of tools we will use there for looking for at performance. One is actually benchmark.net, or in some cases, we have some benchmarks that aren't very well suited for benchmark.net, big macro benchmarks where you're trying to test like a distributed system. That's not, benchmark.net's not built for that. It's built for
Mhm.
measuring much smaller stuff, like much closer to the metal type issues. For our big macro benchmarks, we'll run them in debug mode with the dynamic profiler and writer attached to it. And we've actually found numerous performance improvements as a result of that. Stupid things like boxing allocations and stuff
Mhm.
like that show up on there. Where that probably wouldn't ever, you would never see that really in memory because those objects are all getting like GC'd, right? So it's all Gen 0 garbage collection. So you might see that on the spikiness of the chart. But if you let the thing run for a long period of time, it's not going to show any leaks. Having the dynamic profiler and writer tell you, hey, this line of code is kind of allocated. You might want to take a look at that. That's another thing that we use quite a bit.
Mhm.
Memory is more of our tool that we use for when we know there's a problem. And now we need to figure
Mm.
out where it's happening essentially. So it's kind of
Yeah.
like the stage two of the diagnostic process there.
This is one of the problems us as tool vendors, profiler vendors, actually face is that profilers are often used reactively. So, oh, I've got a
Exactly.
problem. Let's go and figure it out. By which point, it's kind of too late. You know, as you say, you've had an issue during development. During production, which you ideally would have wanted to fix during development. And the dynamic profiling you're just mentioning there, I presume that's the dynamic profile, the DPA. What does DPA stand for, Sasha? Dynamic Profile Analysis? Yes.
Dynamic
Um,
program analysis.
Program analysis. There it is.
Mhm.
Yes. And this is the thing which monitors your code as it's running just in a normal everyday development scenario. And it's got a number of automatic inspections. So to look for known issues or, too much memory traffic, too long database queries and things like that.
Yeah, the dynamic profiler, or sorry, DPA, we'll call it. The DPA is awesome because it basically gives you some of that diagnostic hints while you're doing everyday
Mhm.
development tasks. So we proactively use that running like our remoting benchmarks, for instance, which is kind of like the most performance sensitive area of Akka.net. We also use, I think we've used the dot trace. What's it called? The dot trace exporter for benchmark.net before is something
Mhm.
else we've used, looking mostly for
Oh, yeah, that's
CPU
cool.
issues
Mhm.
there. And then we also use in benchmark.net some of their memory analysis tools where we know we have memory sensitive, like hot allocation paths. Good example, the code for spawning actors, where the actor has to create a mailbox, which is like a concurrent queue, and there's a couple of other little data structures it needs. We try to keep that very religiously under like 1 kilobit per actor. Because you can have processes that have tens of millions of actors in them that are doing lots of parallel processing. So we've got to keep that memory footprint kind of measured and under control. So benchmarking is usually the first line of defense against a lot of that stuff. The profiling tools all kick in when we're either looking for things we don't know or problems. That's where the dynamic program analysis helps a lot. And then the stage 2 is like, well, if a bug gets reported, that's when we'll bust out dotMemory and dotTrace to start trying to really hammer on stuff in here. So I think kind of a holistic approach to all of that is really benefited us and our users pretty well.
Yeah, don't worry too much about the whole DPA thing. We're moving much more of that into the monitoring tool window as well, so it's just going to confuse things even further. But the monitoring tool window is the place to go. But I wanted to agree. Big shout out for benchmark.net. It is a fantastic tool to use for this kind of thing. And you mentioned the exporter for dotTrace as well. That's a very useful feature to be able to sort of capture traces and open them up in dotTrace afterwards, which is really cool. Sasha, I think you had another question.
Actually, I have a question from the chat. How do you think OpenTelemetry integration with Aspire will impact this type of profiling in the future?
It won't. Basically, so we've got an OpenTelemetry product. I've been doing, like, let's say, distributed systems observability stuff since before OpenTelemetry was a thing. It was all with open tracing and other stuff before that. What open tracing can really help you with, not open tracing, sorry, OpenTelemetry tracing can help you with is figuring out latency and where things timed out, which is in itself a very useful class of diagnostic tool, but it doesn't overlap very much with like memory, CPU, and performance concerns as much. It's more of a, how do I put this? Tracing can help you figure out if you have a latency problem. Everything we've talked about here can help you figure out what might be causing it. So they have a relationship, but one's not a replacement for the other necessarily. On the metric side of things, this is where OpenTelemetry is a little bit more interesting. The .NET runtime has been getting better and better at surfacing some of the garbage collection metrics and some other, not CPU utilization, but other things that are a good proxy for it, such as, for instance, you can get a pretty effective measure of how long the .NET thread pool's queue is at any given time, which tells you if you're starting to see, like, essentially back pressure forming inside your system. I actually open sourced a Grafana dashboard maybe 4 months ago that kind of helps visualize a lot of that with Grafana. That is another area where OpenTelemetry can actually contribute a lot. But the metrics it can give you are things that are relatively cheap to measure. Being able to do things like figure out what's the hot path in your call stack is expensive to measure. And that's where you need a more bespoke tool like dotTrace or something to kind of help you answer that. So these tools do work together in concert. If you notice, for instance, looks like our .NET task pool, our .NET task queue length is like spiking pretty hard when these things are happening in our system. That tells you, kind of gives you like a direction you need to go in. A tool like dotTrace will help you kind of unpack why that might be the case, you know? So the one's not a replacement for the other. They're definitely more synergistic in that respect.
Thank you so much for your perspective. I think we have time for one more question. Matt, do you want to read it out?
Yeah, sure. So another question from chat. It's can memory leaks detected using AI coding, such as Copilot and Cursor? Will they kind of keep? What am I saying here? Can memory leaks be detected using AI and stuff like that, or are we still going to be using tools like dotMemory for quite some more time? Do you think?
That's a great question. So I wouldn't call myself an AI maximalist, but I have definitely been going pretty hard in the paint, as the kids say, um, with using tools like Claude Code and others to kind of work on Akka.net. One thing I know that AI tools can do an awesome job finding is race conditions. I've probably in the past week knocked out about 20 of those in the Akka.net test suite.
Wow.
So they're really good at finding those. The trick to making any AI coding workflow function correctly in a reasonably complex piece of code is you have to have a deterministic process or a reasonably deterministic process for beating the weakness out of the AI's inference. Namely, the AI is going hallucinations are basically just a function of the statistics. It's the math that your agents use. They're going to make stuff up and not get everything right. You need to give it a feedback loop that can be run more or less automatically to help give the AI additional inputs back. That's where a
Mm.
tool like dotMemory is going to be really useful for trying to find resource links or performance issues in the future. Is the AI can suppose lexically by literally looking at the text of your code. Most of the time, they're not even looking, like getting language server LSP, language server process feedback back at all. They're literally just lexing the textual symbols, not even the actual compiled symbols, to try to figure out how your code works. And they can do a pretty amazing job with that, but without giving them some sort of black and white hard feedback to basically say, no, this didn't work, or yes, it did. It's just going to be essentially making very smart sounding guesses that are in all likelihood probably wrong. So I don't think AI is going to replace a tool like dotMemory or dotTrace anytime soon. I think what would be better would be building a process where AI can try something, run dotMemory, and then analyze the dump afterwards. And you basically kind of let that cook on a, GitHub Action runner or on a server somewhere for, I don't know, it might take hours for it to come up with something where it might be able to find some ways to say, hey, I was able to reduce memory consumption without breaking any core functionality. And I used your test suite and I used dotMemory to verify that I did that. Yeah.
So
Um,
synergy, not replacement.
Exactly. Synergy, not replacement, where the AI tooling really needs some second method of verification for figuring out if it's done good or bad. And test suites and compilers are sort of the most basic set of things we have for that today. But a tool like a profiler, where it has the ability to interrogate the results inside the dotMemory output, might help it find things like this in the future. I think that's mostly today an exercise and being able to get something like Claude to understand dotMemory's output. Actually getting it to launch dotMemory and run it probably can do that. Getting it to make sense of information it gets back is probably the challenge today.
I think that sounds like a great idea to me too. We're going to have to wrap it up there. I could talk to you for ages about this. I think. Thank you very much for your session. Thank you very much
Thank
for
you.
your questions and answers afterwards. And I'm looking forward to seeing the talk about using AI to get rid of race conditions.
Oh boy, I guess I'll need to work on that a little bit more. All
Fantastic.
right.
Thank you very
Thank
much, Aaron.
thank you. Bye bye.